Should we
can
start?
start. Yes, okay, you can start, Anthony, please.
Okay, so it's my great pleasure to introduce you today our speaker is Alicia Tocino from the University of Málaga, who is going to talk about tensor product of evolution algebras, which is a joint work with Yolanda Cabrera, María Dolores, Martín, and Cándido Martín. So, please. You are mute, Alicia.
Now.
Now.
Okay. And now I have to put this again. And now it's everything under control, I think. Well, thank you very much, Antonio, for the introduction, and thank you for the invitation. I'm going to talk about the tensor product of evolution algebras, and as you said, it's a joint work with Yolanda, Dolores, and Cándido. Okay, so the contents of the talk are the following. First, we will talk about some preliminaries on evolution algebras and graphs. Then we will speak about the tensor product of algebras and of evolution algebras. Then we will give some properties of the tensor product of evolution algebras, and we will focus on dimension 4 and dimension 2. Next, we will give some definitions of the directed graph associated to a tensor product of evolution algebras. And finally, the most interesting part is the part where we classify the perfect tensor product of evolution algebra. So let's start. Evolution algebras are a kind of evolution algebras that Tian wrote a lot, and they are a kind of gametic algebra, which is that model self-reproduction in non-Mendelian genetics. So if we have Mendelian genetics, then we can consider the alleles E and E as the vector of the basis of our algebra. And we can give the multiplication table of each of them. And in the case that when we multiply A1 with A2, and we have a 0 here and a 0 here, this is the case of the evolution algebras. So when the multiplication is always between any two different, is always 0. And this is the starting point of the gametic algebras and of the evolution algebras. It has much more applications in biology and in stochastics problems and so on, in geometry, in physics, a lot of things. Well, I will all the properties and all the definition that I'm going to use, most of them are in the doctoral dissertation of Yolanda Cabrera Casado that make her PhD in evolution algebras. And she also published 2 papers together with Mercedes Siles Molina and Canumi and Maria Victoria Velasco that were her advisors in the PhD. So we will say that an evolution algebra over a field K is a K-algebra provided with a basis such that the product of each 2 different elements is 0. And such a basis is called a natural basis. Just to comment that evolution algebras are commutative evolution algebras, and we are going to use it before. Okay. Since we have only the product of each element on the basis with himself, and if we put this product like a linear combination of all the elements in the basis, we have here some constant that we'll call structure constants. And we can construct a structure matrix from these constants. And there is a relation between the matrix associated to an evolution algebra with respect to the basis B or with respect to the basis B prime, or both of them natural basis. And the relation is this one, where this square here is the Hadamard product. So we have to put the square in each of the elements. As an example, we have an evolution algebra with a natural basis that we call B1, B2, B3, and with this product. So we have here 2, B2, B1 plus B3, and B1. So the structure matrix we constructed by columns, and we have here 0, 2, 0, since we have here a 2, and B1 and B3 does not appear here. As again, 1, 0, 1 and 1, 0, 0. If we consider a matrix like a change of matrix of basis matrix from the basis B to B prime, then we can construct a new basis B prime using the product, the relation that we have just above. So we have that the new vectors, the new elements in the basis satisfies this new condition. So they are not the same as before, but they define the same evolution algebra. Some remarks is that evolution algebras are not power associative, and therefore they are not associative algebras. So this is why I'm here. And we say that an evolution algebra is non-degenerate if it has a natural basis such that all of the elements squared are different from 0. And this Yolanda, in his PhD, proved that this does not depend on the chosen natural basis. Another definition is the annihilator of A, and is denoted by an, and are all the elements that satisfies this, no? But El Duque Labra, in the paper Evolution Algebras and Graphs, proved this equality. So we can construct the annihilator of an evolution algebra like the span of all the elements in the basis such that the square is 0. And as a conclusion, we have that an algebra is non-degenerate if and only if the annihilator is 0. This is well known. Okay, another definition that we will use is simple. So we have that an algebra is simple if the square is different from 0, and 0 is the only proper ideal. And we say that an algebra is perfect or regular if the square is equal to A. So in the case of evolution algebras, the perfect case means that the determinant of the matrix, of the structure matrix, is different from 0. It can be proved that a simple evolution algebra is perfect, but if we have a perfect evolution algebra, then we don't know if it is simple or not. This is not true. Another definition is that a reducible evolution algebra is an evolution algebra that can be decomposed as direct sum of two non-zero evolution algebras. And if it is not the case, then we call it irreducible. Now we are going to define something that we are going to use through the talk, that is these inner products that can be obtained from the multiplication of a commutative algebra. Okay, so we are going to use the paper simultaneous orthogonalization of inner products over over arbitrary fields from Yolanda Cabrera Casado, Cristóbal Gil Canto, Dolores Martín Barquero, and Cándido Martín González. If we have a n-dimensional commutative algebra with basis B, we can write this product of two elements of A, and this provides the family of inner products, okay, relative to the basis B. So from these inner products, we can define the gram matrix of these inner products, also relative to the basis B. And since we are going to define a lot of matrices, we are going to take the same basis for all these inner products. So all the matrices are constructed with the same basis. I will use this later, and we are going to construct some of these matrices in some concrete cases. Moreover, we are going to need the concept of the set of zeros of an ideal of the polynomial. So if we have the polynomial K-algebra in the variables x1, xm, and if we have an ideal of this polynomial, then we define by the v of h the set of zeros. So they are all the elements in Km such that this polynomial is zero. We need to know when an algebra is an evolution algebra, since we are going to take two evolution algebras and we are going to do the tensor product, and we want to know if this tensor product is an evolution algebra or not. So we have to, we can prove it in two different ways. The first one is regarding the evolution test ideal. So for this purpose, we are going to define the polynomial K-algebra with these variables, and we are going to consider the ideal I generated by these polynomials. There is an example that we are going to construct these polynomials. And we will call the ideal I the evolution test ideal, since this ideal gives us all the information that we need to know if we want to know that A is an evolution algebra or not. So the set of zeros of the evolution algebra detects when an algebra is an evolution algebra by the following criterion. If the set of zeros is not empty, then it's an evolution algebra, and conversely. So what we are going to do in order to see that the sets of zeros is different, is not empty, is to compute the Grosvenor basis of the ideal. And we are going to check if one is in the ideal. So in this way, we have that A is not an evolution algebra. But this computation of the reduced Grosvenor basis of an ideal becomes impracticable as the dimension of the algebra increases. And this is one of the tests that, as I said before, Yolanda, Cristóbal, Dolores, and Cándido described in this paper. Okay, so how can we use it? We consider a K-algebra, a characteristic equal to, and a basis E1, E2, such that, and we have all the multiplications, E1 square, E1, E2, E2, E1, E2, E2. Okay, And we are looking for a natural basis, B prime, such that we can write U1 as a linear combination of E1, E2, and we write U2 as a linear combination of E1, E2. Okay. We need that this is 0 in order that the basis becomes natural. So we have to impose it. And this is how we construct the polynomials that we have in these slides. This is the second polynomial that we are going to use, and this is the first and the second. There are two that are the same, since we have that the product of E1, E2 and E2, E1 is the same. So this is one of the polynomial that we construct, and this is the other one with the set. The first one, this is the first one. This is P0. So we have the evolution test ideal of A, and is this, and we compute the reduced Grosvenor basis of the ideal, and we obtain that it is not 1. So if it is not 1, then our algebra is an evolution algebra. Nice. It turns out that this algebra that we are using is the algebra A2 that appears in the paper, The Variety of Two-Dimensional Algebras over an algebraically closed field of Ivan Kaigodorov and Volkov. Indeed, we are going to use all the elements that appear, all the algebras that appear in this table, we are going to use it through all the work. Moreover, to compute the Grosvenor basis, we use the software Singular under the computation of Picasso, that is observer from the University of Málaga. Okay, now the second form that we can, in which we can discover if an algebra is an evolution algebra or not. This is described in the article Determining when an algebra is an evolution algebra of Bustamante, Mellon, and Velasco, but this is only when the ground field is R or C, and also is described in simultaneous orthogonalization of inner products in infinite dimensional vector spaces, but for a general field. And this last one is from Yolanda Cabrera Casado, Cristóbal Gil Canto, Dolores Martín Barquero, and Cándido Martín González, which is a continuation of the previous one. So here in this one, we consider the n-dimensional commutative algebra with the inner products that I have explained before, and the main theorem, the main property that they give is that A is an evolution algebra if and only if the set of inner products that we have defined before is simultaneously orthogonalizable. That is, that there is a basis of our algebra such that all the matrices associated to each inner product is diagonal. So we have to obtain we have to discover if all the matrices can be simultaneously diagonalizable by congruence. So the question is that if given a set of matrices that represents the inner products of each component with coefficients in our field, okay? So under which conditions is there an invertible matrix P such that all the matrices of this form are diagonal matrices? And they define a method in order to see if such a invertible matrix P exists or not. So if one of the matrices that we have is non-singular, so for instance M1, then we construct this product, all of these products, and if all of them are diagonalizable and commute, then we conclude that these matrices are simultaneously diagonalizable by congruence and conversely. But for characteristic equal to, we have to do some specific things, but that's not. And in the case that all the matrices in the set are singular, then they found a reduction to the previous case. So the main thing is that we have to construct these matrices and we have to check if all of them are diagonalizable simultaneously. Okay, next. We are going to use also graphs, in the directed graphs. So we are going to take the set of vertices, the set of edges, the source, which is a map, and the target, which is another map. Okay. And we defined the target and the source of F as if we take an edge in the set of edges, the target of F is, so if this is F and we have 1, 2, so the target of F is 2 and the source of F is 1. Moreover, we have the adjacency matrix, which is filled with the numbers of arrows of edges that goes from I to J. So in this case, in this example, we have the adjacency matrix, and this column represents that this row represents that from the vertex 1, there is an arrow that goes to vertex 2 and vertex 3. But if we have also a 1 here, it should be also an arrow here, a loop. Okay. So we have the relation between evolution algebras and graphs that a lot of properties were given in the paper Evolution Algebras and Graphs by El Duque Labra. So the first one is the notion that of directed graph associated to an evolution algebra relative to a basis. So we have an evolution algebra, we have a natural basis, we have a structure matrix, we have the structure constants, and we want to construct the adjacency matrix. How do we construct this? So the elements in this matrix are 0 if the structure constants are 0. And the elements are 1 if this structure constant is different from 0. Moreover, since we are going to consider only 1 here, we are going to consider graphs with at most 1 arrow between 2 vertices. It could be the same vertex, so we allow loops here. Another definition that we are going to use is the definition of strongly connected. So a directed graph is strongly connected if given 2 different vertices, there exists a path that goes from the first to the second one. And there is a characterization of evolution algebras that says that an evolution algebra is simple if and only if its associated graph is strongly connected. And we're going to use it also. So as an example, we have our evolution algebra as before with the structure matrix as before. And we are going to construct the adjacency matrix. So we have to put here 1, and we have to transpose. This is how we construct it. And we can write the graph associated to this adjacency matrix. Moreover, one can check that the evolution algebra is simple since the graph is strongly connected. How can we prove that the graph is strongly connected? So if we compute the power of the adjacency matrix and we change each number that is different from 0, we change this number for 1 and we do the computation. If we arrive until some k in which the power matrix is filled with 1, all of 1, then we have that our graph is strongly connected. And we use it also. We indeed define this k as the stabilizing index or in our paper. Okay, some generalities of tensor product of vector spaces. We define the tensor product as follows. Here we have the dual space of these vector spaces. So F goes from V to K, and this is an element in K. Okay. And if we have B1 a basis of B and B2 a basis of double B, then we can construct the basis of the tensor product as these ones. So in a natural way. We are going to define a product on the tensor product to construct an algebra, and the product is defined in a natural way. So we multiply component by component. We say that algebra is tensorially decomposable, which is what we want, if it is isomorphic to the tensor product of two algebras with dimension greater than 1. Otherwise, we call it indecomposable, tensorially indecomposable. Moreover, we translate this term, tensorially decomposable, into matrix. So we say that a matrix is tensorially decomposable if it comes from the Kronecker product of two matrices. Okay, next. In the case that we have that both matrices are perfect algebras, then the tensor product is also a perfect algebra, and conversely. In the case of simpleness, we don't have both implications. We only have one. If the tensor product is simple, then each of them is are simple algebras. We are going to prove that the other implication is not true. So we are going to consider a field with characteristic different from 2 and an algebra with basis E1, E2, and multiplication E1, E2 is equal to E2, E1 equal to 0. So it is indeed an evolution algebra, but we don't care here. E1 square is E2 and E2 square is E1. So it can be checked that A is simple. Okay, so A is simple. However, we can construct in the tensor product algebra, we can construct this ideal, and it can be proved that it's an ideal of the tensor product. So the tensor product is not a simple algebra. More properties of the tensor product. So we want to answer the question under which conditions being evolution algebra is inherited from the tensor product to the factors. Okay, so in order to answer this question, we have to define what is a locally non-degenerate algebra. And it turns out that a locally non-degenerate algebra is such an algebra that has a basis that verify that some of the inner product that we have defined before is non-degenerate. And since we are going to focus on two-dimensional or four-dimensional evolution algebra, if we have a two-dimensional evolution algebra that is perfect or whose dimension of the a square is 1, but the annihilator is 0, then these ones are locally non-degenerate. This will be useful in our classification. But the main theorem by now is that if we have two evolution algebras, then the tensor product is also an evolution algebra. Moreover, we can construct the natural basis in terms of the natural basis of A1, A2. Conversely, if we have A1, A2, two commutative algebras and A1, A2 finite dimensional evolution algebra, if A1 and A2 are locally non-degenerate, then we have that they are evolution algebras. Okay. So the structure matrix of the tensor product of evolution algebra is of evolution algebras is given by the Kronecker product of two matrices. So if we have the structure matrix of A1 and the structure matrix of A2, then we make the Kronecker product of these two matrices and we get directly the structure product, the structure matrix of this tensor product. Moreover, the same relation between the matrices of the with respect to different bases is true. So we have here the Hadamard product, and we have P and Q, the change of basis metrics from B1 to B1 prime, and everything works fine here. Now, I want to show an example which is illustrative, since the decomposition of an evolution algebra into tensor product is not unique. So what I'm going to show is that we have one evolution algebra of dimension 4, and it splits into forms. One of them with the two of them evolution algebras, and the other one none of them evolution algebras. Okay, so for this example, I'm going to use the algebra B3 of the table 1 in Kaigodorov and Volkov with a field of characteristic different from 2. So this algebra is a two-dimensional algebra with basis E1, E2. E1 square is equal to E2 square, which is equal to 0, and E1, E2 is equal to E2 and is minus E2, E1. Okay, it can be checked that A is not an evolution algebra as you want. We have the simultaneous overtotalization or the evolution test ideal. We have done it through the evolution test ideal. We have constructed the evolution test ideal of this algebra, and we have proved that one is in the ideal by computing the reduced Grosvenor basis. Okay, so A is not an evolution algebra, but we compute A times A, the tensor product, with the basis defined in a natural way with this multiplication. Okay, but we can find a natural basis And the natural basis is defined in terms of the basis that of U1, U2, U3, and U4. And this is a natural basis. Indeed, we have the structure matrix of A associated to the tensor product relative to the basis B here. And it can be checked that this structure matrix is tensorially decomposable since it is the Kronecker product of two matrices of dimension 2. So we get finally that our algebra A is tensorially decomposable. Now we start our study focus in four-dimensional tensorially decomposable evolution algebras. So what we did is we took all the two-dimensional commutative algebras that gave Kaigodorov and Volkov, and we used the procedure of simultaneous orthogonalization to recognize which of them is an evolution algebra. Okay, so we have made this computation, and we have thus, for instance, A1 is perfect evolution algebra. It is not an evolution algebra, it's an perfect algebra, and is non-simple. Next, we have that A2 is an evolution algebra, is non-perfect, and is non-simple. And we do this with all the two-dimensional commutative algebras. So we made a classification. And what we did also is to check if the tensor product of any two of them is an evolution algebra. And in the positive case, we verify if it is simple or not, so we can detail the classification. As an example, we have the in characteristic different from 2. This algebra with this basis, E1, E2, and this multiplication, E1 squared is E1, E1, E2 is this, E2, E1 is this. It has to be commutative, so E2, E2 is E2. And we compute E3, the tensor product of E3 with himself. And we want to know if this is an evolution algebra or not. So with the basis given by all the tensor product of all these bases in E3, and we compute the product between any two of them. We start, I have only given the first of them, so I have here always E1 times E1, E1 times E1, E1 times E1, E1 times E1. We should have to continue. So, but this is just to let you know how this work. So we multiply by all of them, and we compute. So the inner products that I have been talking about at the beginning of the talk, that gives the gram matrices M1, M2, M3. So how can we construct the matrices from this product? Since we have computed, this is fixed, we only can compute the first column of M1, M2, M3, and M4. And the first column of M1 is given by the coefficients of A1 times E1. So we have here 1, and in the next we have gamma half. In the next we have gamma half, and also we have gamma square divides by 4. So this gives the first column of the matrix M1. If we want to compute M4, then we have to focus on E2 times E2, and we take the coefficients of E2 times E2. The only one that survives is this, and this is how we construct this. Analogously, so we can get the rest of the products and the rest of the columns. So the gram matrices of the inner products are the following: M1, M2, M3, and M4. We get that M1 times the inverse of M2 is not diagonalizable. So we have to the algebra that we were working on is not an evolution algebra. So we have that this is not an evolution algebra. And using the same technique, we prove a lot of them. We prove that all these are not evolution algebra. We can put together all the information of the four-dimensional case, and if the field is algebraically closed, and we have that the tensor product is four-dimensional and is simple, in the case that it is simple, evolution algebra, then we have that both factors has to be evolution algebras. Moreover, if we have A1 and A2, two k-algebras with K an algebraically closed field and characteristic different from 2, and A1 times A2 is a non-trivial evolution algebra with dimension 4, which is the case that we are talking about, and both A1 and A2 are commutative algebras, then both of them are evolution algebras also. Okay, more things. Regarding the non-degeneracy, this is the natural thing that happens. If A1 tensor A2 is non-degenerate, if and only if A1 and A2 are both non-degenerate, and this equality holds regarding the annihilator and the tensor product of two algebras, of two evolution algebras. Now we talk about the graphs associated to the tensor product evolution algebras. We take a lot of information of this paper on the product of directed graphs of McAndrew. They define there the categorical product of two graphs, and the most intuitive way to think about the categorical product of two graphs is about the adjacency matrix of the graphs. So the adjacency matrix of the graphs G1 times G2 is the Kronecker product of the adjacency matrices of the G1 and G2. Moreover, in the same paper, McAndrew gave a result regarding the number of connected components of the categorical product of two graphs. And we used these results and more things in evolution algebras and graphs of El Duque-Labra to prove that if G1 and G2 are strongly connected, directed graph, and we have closed paths of coprime lengths, this is to use these results, then the tensor product of A1 and A2 is non-degenerate and its associated directed graph is connected. So we also have that A1 times A2 is irreducible. Conversely, if the tensor product of two evolution algebras is non-degenerate and irreducible, then each factor is non-degenerate and irreducible. The most interesting part, we arrived finally. So when a perfect four-dimensional evolution algebra is tensorially decomposable into two evolution algebras, we have a first property that says that if we have A1 and A2, two evolution algebras of dimension 2, if the tensor product is a perfect evolution algebra, then or A1 and A2 are simple, or one of them is an evolution algebra. And we use this in the proofs or the main results of this section. So how do we prove that an evolution algebra is tensorially decomposable? We do that now in terms of the structure matrix. So we want to answer, how do we prove that the structure matrix is tensorially undecomposable? Okay, so we have a perfect four-dimensional evolution algebra with structure matrix M, and we prove that there are several invariants of the evolution algebra that gives us the information to decide if M is tensorially decomposable or not. Okay, these invariants indeed are given in the PhD thesis of Yolanda Cabrera. And these invariants are the numbers of zeros on the structure matrix. This means the number of columns filled with zeros, and this the numbers of rows filled with zeros, and this the numbers of zeros in the diagonal of M. So if we have that, or the zeros of M is one of these, rank equal 3, it has one column filled with zeros, or one row filled with zeros, or one zero in the diagonal, then M is tensorially undecomposable. We are going to apply this to the next example, and we consider M this matrix. We count the numbers of zeros in M, and we have 1, 2, 3, 4, 5, 6. Okay, 6. So 6 is in here. So we have that A is tensorially undecomposable. In the second case, for N, we have that the zeros is 7, the rank is 4, there is no column filled with zeros, no row filled with zeros, no element in the diagonal 0. So we don't know. We don't know if this matrix corresponds to a tensorially decomposable evolution algebra or not. Moreover, one can check that a matrix is tensorially decomposable in terms of the extended matrix. If the rank of the extended matrix is 1, then the matrix is tensorially decomposable, and conversely. So for the classification of four-dimensional perfect evolution algebras, we need the important fact that perfect evolution algebras have essentially one natural basis up to permutation and multiplication by a scalar. So thanks to this, we have that a perfect evolution algebra, dimension 4, is tensorially decomposable if and only if there exists a structure matrix, well, a matrix in the orbit under the action of the symmetric group of order 4 of one structure matrix of A, such that the rank of the extended matrix is 1. What are we going to use here? We are going to use the paper Squares and Associative Representations of Two-Dimensional Evolution Algebras, given by María Inés Cardoso, Daniel González, Dolores Martín Barquero, Cándido Martín González, and Mercedes Siles Molina. There, they determine the structure matrix or perfect evolution algebras of dimension 2. Since the structure matrix are essentially the same up to permutation, so we have only 3 types. And what we are going to do, we are going to make the Kronecker product of each 2 of them and analyze what we obtained. It turns out that we obtained 13 different types of 4-dimensional tensorially decomposable perfect evolution algebras, and we can classify them in some set of invariants that are the numbers of zeros in the matrix, the numbers of zeros in the diagonal, and the simplicity, if it is simple or not. The other one is the number of zeros in the matrix and the characteristic polynomial of the structure matrix. And finally, the characteristic and minimal polynomials. So in our paper, we give a table just like this, but with 13 rows. And we define the number of zeros of M1, of M2. We construct the tensor product. We say if it is simple or not. We count the numbers of zeros of the Kronecker product. We construct the characteristic and the minimal polynomial, and 13 different types of perfect evolution algebras arise. Finally, I want to show an example. We have that A is an evolution algebra with a natural basis B and with this structure matrix. And we want to know if I can write A like A1 tensor product A2. I don't know. So first, what we are going to do, we are going to count the numbers of zeros, the rank, the numbers of columns filled with zeros, the numbers of rows filled with zeros, the number of the zeros in the diagonal, and this does not give anything. So we have to go further. So we start and we say, is A perfect? The determinant of the structure matrix is different from 0. So yes, okay. Is A simple? So since it is perfect, we can apply. We know that it has to be inside here. It has to be one of them. So we have to complete if it is simple or if the characteristic and the minimal polynomial. So we have to answer if it is simple. We compute the associated directed graph and check that is not strongly connected. In the same way, we compute this is not a name, this is a name. Well, we compute the powers, and we have to this power of matrices stabilizes, and if the final matrix is filled with 1, then it is strongly connected. Okay, in this case, no, we don't have. It is not simple. So since it is not strongly connected. More, we want to know if A is tensorially decomposable. So we have to check the last thing, the rank of the extended matrix. We compute all the elements, all the matrices in the orbit of M under the action of S4, and we get that one matrix, M prime, which is this, can be written in terms of the Kronecker product of 2 matrices. So the extended matrix has rank 1? So the answer is yes. Moreover, the characteristic polynomial is this one. So we go to the table and we check which types has this characteristic polynomial. We only have two, this and this. And we compute also the minimal polynomial and we check that this. So we have that it can only be the sixth type. So we have given a lot of tools to know if a matrix, if an evolution algebra is tensorially decomposable or not in different ways. And this is all that I wanted to talk about. Thank you very much for your attention.
Thank you very much, Alicia. Now, is anybody in the audience who have a question for Alicia? Somebody? If not, I have a few of them.
Okay.
But okay, so I will yeah, at least one. So at the beginning, you said that when you got two algebras, A and B, and you make the tensor product, there is a way you can recognize whether A tensor B is, and you know A tensor B is an evolution algebra, so there is a way you can recognize whether A and B are both evolution algebras, right?
Yes, I think so.
Yes, and then is there any correspondence between the basis you have in A tensor B and the tensor basis from A and B? I mean, if you have an natural basis in A tensor B, you can always claim that that basis comes from a basis of A.
No, I understand you, Antonio. It is interesting. I don't remember if we have work about it or not. I don't
I mean,
remember.
you can choose one, right? Which
Yes.
is coming from the tensor product. But I wonder whether any one that you already have in A tensor B comes from a tensor product base.
Yes. No. I think that we have not given an answer of that question, but that question sounds in my mind. So we have thought about it, and I think that we did not get a concrete result. So
okay, and then in the list of evolution algebras in dimension 4, you get 13, which are tensor decomposable. But how many of them are of dimension 4? Do you know how many?
all of them. All of the 13 that we obtained have dimension 4.
But think of the evolution algebra as a symmetric monoidal category. So you can think the algebras as, you can construct a ring out of the algebras, right? Where the addition is just the direct sum, and you have a kind of a formal subtraction, and then the product is given you by the tensor product, right? So then your theorem is saying something about whether or not you can factor in this graded ring. It's a graded ring in the sense that the graduation is a super ring, in the sense that the dimension is given to the grade of every object. So is there any object in degree of dimension 4 which is can be factorized, or is this composable? Is there any new generator in this ring in dimension 4 or not? Or is there any four-dimensional evolution algebra which is not in this is not decomposable, tensor decomposable?
I don't know, Antonio. I cannot answer you right now. I have to think about it. Yeah, I have to write it. So
okay.
But I don't have an answer. I'm sorry.
So, any other questions from the audience? No? No. So, if not, thank you again, Alicia.
Thanks to you.
Was a nice
Thank you for your attention. Thanks. Bye.
Bye-bye.
Bye.